it is my pleasure to call Giulia Galli to give the talk of which you see the title, so I will not repeat. You know your times, and you are very welcome to start.
All right. Thank you. Good morning. And it's a real honor for me to be here this morning, and of course, a real pleasure. And I'm really happy to be here to wish CECAM happy birthday. And I've been fond of CECAM and the CECAM workshop since the beginning of my career. And my first CECAM workshop, the first CECAM workshop I attended was in Paris 30 years ago, where I also had the opportunity of meeting Carl Moser. And I still remember that meeting. I think it was probably my first invited talk or one of the first invited talks. And I talked about carbon, liquid carbon and amorphous carbon. And there will be some carbon also today in my talk, not that much, but I've been working about carbon on and off for 30 years. So what I would like to tell you today is some of the work that we have done in the last few years about trying to understand materials property and interaction of light and materials for specific applications. And we have addressed two broad areas. One is the area of energy conversion and light absorption by materials, and harvesting of electron-hole pairs to generate currents. Currents that you may want to use to do a chemical reaction and an interface, or current that you may want to use to generate stimuli to, for example, probe specific properties even of a cell. Another area, another area, no, it doesn't work. Another area where recently we have become more interested about is the area of qubits, spin defects. And so manipulation of defects in semiconductors, optical manipulation, to try and understand how to predict material for new computing technologies and also for a new generation of nanoscale sensors. So what I will do in my talk this morning is to tell you about our theoretical and computational strategy to address in a general way all these problems of light-matter interaction. And unfortunately here this pointer doesn't work, but I will try to maybe okay, I have to put, okay, all right. And then I will try to give you an idea without many details about what we learned about structure, function, relationship, and descriptors to predict optical materials for target application. As I said, the target application are photoelectrochemical cells, so absorption of light, for example, to oxidize and reduce water. And they are materials like silicon membranes, p-n junction that you may want to put on top of a certain cell, and then activated by light, they will produce a stimulus to this cell that you may want to use to open some channels or to probe your cell. And another application is optically addressable defects in semiconductors. So for us, these materials are really problems of interfaces and defects. So if we think about a photoelectrochemical cell, we address problem of a photoabsorber interface with a catalyst in contact with water. If we address the problem of a silicon membrane at the interface of a cell, we address the problem of a p-n junction in contact with the metal, you see there is a parenthesis there because we haven't fully solved this problem yet, and in contact with salty water. And if we address defects in semiconductors, we specifically want to address spin defects. And these blue dots are there to tell you that there are always also defects that you don't want. There is not always only the defects that you do want. So let me give you an idea about the general theoretical strategy, and while I present this, I will present examples related to this application. So the structural models of the system that we want to study are usually determined by doing first principle molecular dynamics, and occasionally also atomistic, but mostly first principle molecular dynamics. And there is always some input from experiment there, right? The starting structure or some understanding of the material derived from experiment, although the parameters are not. And then what we would like to be able to do is, once we have a structural model, to do on-the-fly spectroscopy to characterize our materials and to use this also to predict properties of the material. And the idea would be to have, to be able to address a number of spectroscopical properties that are listed here. Some we are able to compute and compare with the experiment and also use for prediction. Some are not yet there. And if you think about the problem of spin defects in semiconductor, there is an extra step and an extra problem that we have to address, which is coherence of spin defects, and hence we have to understand coherence spectroscopy. And this we do at the very end of all this cycle, where we derive parameters from first principle, also from our spectroscopic studies, to build spin Hamiltonians that then we use to do coherence function. And I will tell you a little bit more about this at the end of my talk. So while doing this, there are general questions. I will not have any definitive answer to this question, but these are questions that we address while we use or build our computational strategy. There is always the question, which DFT, which functional? And then when you do spectroscopy, is it more accurate or more appropriate or easier to do time-dependent hybrid density functional, or to use Green's function method? And really, this is one interest of ours right now. How do we build an integrated framework for multiple spectroscopy in a concerted, in an integrated framework, really? So in the last 10 years or so, we have spent quite some time to address the two of the simplest spectroscopic properties of materials that you could think of, related to photoemission spectroscopy and to absorption. We are very interested in photoemission spectroscopy because we want to understand the energy levels that are related to band offset, to how the energy levels are aligned to each other at interfaces. We're interested in interfaces. And just to set everybody on the same page, we solve the equation of density functional theory, and then on top of this, we solve an approximate, very approximate form of the Dyson equation, where the interaction between electrons is described by a self-energy. And if you want to understand the self-energy, you need to understand a so-called screen Coulomb interaction. And there is a big object here, which will be for us for a while in this talk, which is the electronic screening, the screening which connects the bare Coulomb interaction with the screen Coulomb interaction, which enters the approximate form of the Dyson equation. And we have built techniques to compute that complicated object using density functional perturbation theory, and using that theory that was developed starting in 1987 by Stefano Baroni and collaborator, we have been able to solve those equations without any need to explicitly evaluating electronic virtual state, empty states. We have not changed the prefactor we have not changed the scaling of the solution of the equation, which is too bad, of course, but we have changed the prefactor, and we have changed the prefactor in such a way that we have been able to actually access quite large system, large for electronic structure people. If you talk to people used to do for, classical molecular dynamics, this is not that large. But so these numbers, of course, specific number are not important, but just to give you an idea, we can do this kind of calculation for systems that have between 1,000 and 3,000 electrons, depending on whether we want to include spin-orbit coupling, and of course, depending on how many molecular dynamic configuration we want to access. And we do this by using a code that we have developed called WEST, interfaced with Quantum Espresso and QBox, the first principle molecular dynamics code. So recently, we have started changing the way we compute the electronic screening. And we asked the question, can we keep all the good things that came from the use of density functional perturbation theory, no empty states, one single parameter to define the accuracy, but actually address some of the existing drawback. And so what we are doing now is to do molecular dynamics in finite electric fields. And we use molecular dynamics in finite electric fields to compute responses to external potentials that then we use on the fly to compute the electronic screening. And by doing this, we actually can access a number of spectroscopic properties. I will give you examples. And we do this by coupling molecular dynamics and many-body perturbation theory codes in a client-server mode. So the reason why we started thinking about changing the way we do compute external perturbation is to address the following drawbacks of algorithms that we and many others have used to do photoemission and spectroscopy using many-body perturbation theory. First of all, there is an approximation which we call random phase approximation, which amounts to neglecting this derivative here. So when I told you need to compute the screen-Coulomb interaction, there is this big dielectric matrix. If you want to compute that matrix, you need to compute derivative of the effective potential that is in your equation. And of course, there is a part that comes from the exchange and correlation. And we happily neglect it with some hand-waving argument. The other limitation is that it is much more time-consuming and rather difficult to start doing many-body perturbation theory, starting from hybrid functional for a series of technical reasons. So the strategy to address these two drawbacks has led us to do calculation in finite electric field. And if you have a good way and an efficient way to compute hybrid functional, and if you do calculation in an electric field, it is exactly the same difficulty to use semi-local and hybrid functional. And then you can actually not only, and it's not easy to see, but let me tell you, by doing this, it's also straightforward not only to compute a GW, Green's function times screen interaction, self-energy, but also to add other terms that here are called gamma. And you can do this by running your molecular dynamics and every now and then having a finite field calculation and on the fly doing your calculations. So what did we get? Well, we actually got not much of an improvement by going beyond RPA, and we didn't even get much of an improvement by using the next term. And we tested extensively molecules on a set that has become very popular to test vertical ionization potential, electron affinity, and gap. And the improvement was not much, few percent compared to experiment and compared to CCSDT, both starting from semi-local and hybrid functional. We also tested solids, and I call them simple solids because these are not the most difficult oxides and also semiconductors. Minor differences in the results of fundamental gaps, between 3 and 5%. The students who did this and implemented this, I can assure you, he was not happy, okay? By the way, he's an exceptionally good student. His name is Ma He, and he will finish, just to let you know, his PhD in 1 year. But if you think about this for a moment, you also realize that this is good news, in the sense that the terms that we have been neglected for a long time actually don't impact to this level of accuracy what we have been doing. The gain that we had about this are really major efficiency gains in calculations starting from hybrid function. So why is this important? It's important to us, being interested in photoelectrochemical cells and in defects in semiconductors, because having a hybrid starting point is critical to have even a qualitative agreement with experiment in many cases. So let me give you some examples here. So these are oxides. Two of the oxides that we have studied, tungsten oxide and bismuth vanadate, as photoabsorbers for water split. If you don't have hybrid functional, you don't get the first physical important property in oxide, meaning a localization of holes and electrons of the charges when the lattice moves to form polarons. These are different types of polarons. And so if you don't get those, you also don't get the physical properties that you should care about to study charge transport, which occurs by hopping of these polarons in these oxides. And here is an example of the difference in energy level. These are conduction band maximum, valence band minimum, valence band maximum. These are experiments and these are results. If you do GW on semi-local functional, you don't even get close to experiments. And here, this is a more complicated result on a wet defective surface, and these are flat band potential. And again, you need to start from hybrid functional. I will tell you later which hybrid functional this is. Of course, this begs the question, do we really need GW there? What if we just use hybrid functional? I'll get back to that at the very end. And I don't know the answer to this question. There are classes of system for which actually some hybrid functionals are good enough, and there are some others where GW still gives you some correction that are important to compare with experiment. Is this the case only for oxides? If we study semiconductors that we have all happily studied by doing GW on semi-local functional, is the situation different? Well, it's simpler. We have studied functionalized silicon surfaces that are used as photocathode. And by doing first principle and many-body starting from PBE, we have learned a number of very important qualitative trends on, for example, functionalized silicon surfaces. These are the functionalization that people experimentally put on silicon surfaces of photocathode. And we have looked at the structure and the electronic structure in the presence and in the absence of water, and we have learned a number of trends, useful. However, this approximation works well for silicon and for semiconductor, as we knew, but much less well to look at the homolume of water, as we and others have pointed out recently. So trends are good, but if you want interfaces between the semiconductors and water, you do need a better level of theory, even in the case of photocathodes made by just simple semiconductor. We have used the same finite field calculation to do optical absorption. and to solve the Bethe-Salpeter equation. And here, there is another advantage relative to GW, which is actually quite huge. Because we do absorption and we do BSC without including a frequency dependence of the dielectric matrix, we can actually completely avoid the calculation of the dielectric matrix altogether. And it can be just a direct calculation in finite field. Again, not, of course, super easy to see without formula, but that's what happens. And then using a combination of block orbitals, which are the eigenstates of our DFT, and localized and transformed as to be localized in real space, because we have certain overlap integral here that we compute in finite field, we really get a very, very huge speed up in the efficiency. So why is this important? So first of all, by doing so, we acquire the ability to compute absorption spectra averaging over first principle simulation. So for liquid and especially for water, many people, including us, by the way, took one configuration of one MD, computed electronic properties, compare with experiment, and declare victory. That's not the way to go, right? And I will show you an example right away. And also, it gave us idea on how also to compute other spectroscopy, for example, photoluminescence. So let me give you an example of this for water. These are spectra, absorption spectra, computed on different, the orange thingy, different first snapshot for different electronic structure level used to do the to generate the trajectory. These are DFT trajectories. It's a name of it, functional. This is the temperature. These are path integral trajectory derived with the potential, first principle potential LME pole derived by Francesco Paesani at UC San Diego. So now that we can do this calculation, first of all, we see the variability. You know, we are able to generate spectra that are statistically significant. And also we see the variability of these spectra depending on the trajectories, on the level of theory that we use to get the trajectories. By the way, this is not surprising, but it's important that we are finally able to do this. And we can also do finite size scaling because we can do large system. And this, although I won't discuss this here, is just to give you an idea. When you average your spectra, and we did this on a path integral Monte Carlo simulation, this is what you get compared to experiment. It's good, and it's not perfect, right? But it's good, and it certainly allows you to discern between water and ice, and also a lot of the peaks that people have been discussing forever in the literature can be accounted for. So, having understood how to do in finite field this calculation, we also understood how to use the same techniques to do different kind of spectroscopies. And one thing that we are very interested in doing is photoluminescence. This is the first spectrum at a function of temperature, photoluminescence. This is not for a liquid. This is for a defect in semiconductor. This is one of the most famous defects, the nitrogen vacancy negatively charged in diamond, used as a spin qubit. The expert will note shift here that we can discuss. This spectrum at 0 temperature, this is a measurement, was computed before, but finite temperature spectra were not computed before. So let me be completely honest here. This is one of the easiest photoluminescence spectra of defects that you can compute. If you go to other defects, and if you are even getting close to having avoided crossing that Hardy Gross was talking about yesterday between excited states and ground state, life is getting much more difficult for you. But at least for simple system, we can do this. Okay, so I told you that hybrid functional are important, are a critical starting point for at least the application that we are interested in. So which hybrid functional? So many people are trying to derive hybrid. So what's a hybrid functional? It's a functional where the exchange is a linear combination of Hartree-Fock exchange and local exchange. So many people are working on this, and I know this is now very, I will forget people here, but I just want to point out that many, many people are addressing the problem of deriving hybrid functionals for materials prediction and discovery, and many group, and again, I'm sure that I forgot somebody here. So our specific interest was to have a hybrid functional that was as simple as we could think of, but that would work for interfaces. We are always addressing problems of interfaces because they are so important in determining the materials properties. And so a couple of years ago, so as I told you, hybrid functional is a linear combination of exact and local exchange with a certain parameter. We started using a hybrid functional, and this is starting 5 years ago, where actually this parameter is the dielectric constant, epsilon infinity of the material, which is determined self-consistently. This is not a parameter, but it's determined self-consistently, starting for an epsilon infinity, for example, at the semi-local level, and deriving it together self-consistently. And we have also, so if you think about this, this is just treating the screen-Coulomb interaction with the simple possible approximation of the dielectric matrix, which is just the long wave limit of the dielectric constant. Okay, so we have also derived a range-separated hybrid, but this is not that important in this talk. So how does this hybrid do? For dielectric constant, quite well. These are mean absolute error. Quite well for gaps of semiconductors and insulator. Again, here compared to other hybrid functional, and also for molecular crystal. This is absolutely not trivial to get. And these are systems where the dielectric constant varies from a little bit larger, the 1 to 16. So these are very different systems. And this is the variability of gaps. These functional also perform well for an ion level in water. And by well, I mean that this is a comparison between theory and experiment, and there are still, errors of 0.5 eV. So, you need to be interested in trends. So well, almost well. These calculations are much more demanding than this calculation. Each of these points is a molecular dynamic simulation, and these numbers are averages over molecular dynamic simulation for all of these points. Okay, so if you want to use those functional to look at an interface, you have a problem. You have a problem because, for example, we are interested in semiconductors and oxides, where the epsilon infinity varies between 5 and 13. Water is around 2. And also, we want to understand exactly what happens at the interface, the dielectric profile, the electronic thickness of the interface. So one thing that we have done is to ask the question, does it make sense to actually have a local dielectric function and a function that varies smoothly from your semiconductor to your big insulator? And we have found the justification to answer yes to this question by using localized representation of eigenvector of the dielectric matrix. So what does this mean? It means that if you use a spectral representation of your dielectric matrix, as we have done for many years using density functional perturbation theory, and as you can do now in finite field, you have eigenvector of your dielectric matrix, and then you can use unity transformation similar to what you do with one-year function, but here used in a little different way, to actually represent your dielectric matrix differently, and then you can convince yourself, yes, that the local dielectric function is a good physically motivated approximation, and you can have a smooth function which goes from the semiconductor to water. And then we define a functional where instead of having a constant, as we did before, we had a local dielectric profile, and this is an ansatz. So it's physically motivated, but there is no theorem or nothing. It's kind of hand-waving way, physically motivated, very good, as I will show you, but not proven to actually have that form of your dielectric profile. So we can derive this self-consistently, and we do this by doing a minimization of an electric enthalpy functional. So if you don't like the modern theory of polarization, which you should really like because it's actually very beautiful, but if you don't like it, forget about this 2 lines, and just keep in mind that we have a way by computing the polarization in the system to compute this self-consistently, and there is no parameter entering there. And there are similar work that has been done, although not in the same fashion and with some parameter included that I think will be presented later at this conference, a very interesting work by the group of Botti. Anyway, so we have this functional here, where we have this dielectric profile, and how are we doing with this? I think the battery are a little bit gone. Okay, no, it's my computer which is not behaving. Okay, let's see. Okay, so did we break what we had for bulk system with our previous functional, right? With the very, very simple one? No, we didn't. And actually, in some cases, we improved the results. Can we describe 2D systems? We are very interested in 2D system for defects, for spin qubits. I'll get I'll get to this in a minute. Yes, we can describe 2D system, at least some of them. And if you're interested about this discrepancy with experiment, we can discuss this. There is a reason related to how experiments actually were done. And can we, how do the dielectric profile look like, and can we converge them quickly? Because this is important. If we have to do zillions of iterations, this is going to be too expensive. So this is the dielectric profile going from silicon to water for different water silicon interfaces, the one of the photocathode. This is another system, silicon nitride. First of all, it converges very quickly. These are different iterations that we do to converge when we compute the polarization. And here it gives you the value of the dielectric constant of the materials. This is not the dielectric constant of silicon, the true one, because in that example, the slab is too thin. And so it's not converged. We couldn't converge. But it is the correct dielectric function for that model of silicon here. And we have a dielectric profile. And there are no parameters here. There are, of course, approximations. So what can we get? We now go back to our problem. These are band offset. This is silicon. This is water. These are PBE, semi-local functional. Don't get even close to getting the level of water right. And these are our dielectric hybrid. So what we are really interested in understanding is the influence of this electronic thickness. And why is that? These are 2 differently functionalized silicon surfaces that act very differently as photocathode. The system, the silicon and the water are the same in the bulk, and at the interface with all the movement of protons, this electronic thickness varies, and we want to understand how this electronic thickness will influence the property of the materials. The other thing that these are very recent results, I'm telling you what the work in progress is. The other thing is, do we need GW now on these results? So these are GW results for water on top of this hybrid functional. You don't need GW there for water anymore. But life is never simple. And so if you actually do, we haven't completely converged GW on DDH for the full slab. There are systems for which you still have, when you do many-body perturbation theory, differences that are important enough to interpret the experiment. So this is what we are analyzing right now. So to which extent we have the effect of GW on DDH, and to which extent we can use this functional. Finally, though, when we do GW on many, I'm not showing this on the material that we have tested, we have small variation. We have what a perturbation theory should give you, not zillions of electron volts, how we had before on PBE, which didn't quite make sense for a perturbation approach. All right, so what did we learn about photoabsorber and catalyst with all this machinery? Let me not give you numbers and stuff like that, but let me summarize what we learned in the last few years. First of all, certainly we learned that the intrinsic properties of materials are totally insufficient to predict materials for water photocatalysis. The interfaces and the excess charges in oxides gives rise to highly reactive species and interfaces, and if you don't take those into account, you cannot, not only you cannot predict, but you cannot even understand experiments. And this is an important finding, in my opinion. So this is what you have experimentally. You have a photoabsorber, a catalyst, which is a total mess, and water goes in between. If you don't take into account a three-way interface, water, the absorber, and the catalyst, you do not understand contacts. To understand, okay, I'm really late, but okay, 5 minutes. So you don't understand whether you have ohmic contacts or Schottky barriers, and you don't understand recombination. So when we understood this, we also understood how really important catalyst morphology was. Electronic properties at finite temperature, including fluctuations, are incredibly important. We have studied examples. One of this is tungsten trioxide, but there are others. And actually, the first example of this was published in the literature about 8 years ago by Annabella Selloni for titanium oxides. The finite temperature property of the surface may be very different, even in the absence of water, from surface property at T equals 0. So if you actually spend zillions of hours minimizing, which we also did, by the way, not only other people, of course, your surface at T equals 0, you may not understand even qualitatively what's going on. And then fluctuations. Fluctuations are really important, and there are these are the fluctuations that give rise to highly reactive species at the interface, and if you don't do a dynamical treatment of your system, we claim you don't understand what's going on. Okay, so basically, the interface is still the device, as it was for semiconductor heterojunction, and defects really take center stage. So how do we probe chemical modification of interfaces and charge transport? I will give you an example, and I will talk now very fast, and the example is about vibrational spectroscopy. So by doing molecular dynamics in finite field, we have access now to the screening. We can have access to the dielectric profile for the hybrid functional, but we can also, and this we and others have been able to do for a long time, compute polarization and polarizabilities to do vibrational spectroscopy. And this is what we have done for this interface here, related to the membrane to probe channels in cells. And we have asked the question, what are the signature of what happens at the interface in the presence of bias? You have a p-n junction, you shoot light, you have a bias at your interface. And we have compared with the experiments, and we did exactly the same thing as done experimentally. They measured IR in the absence of bias, IR in the presence of bias. We computed IR for a non-biased surface and IR for a biased surface. And we have preliminary results that are actually, we have preliminary results that are consistent with experiment. Of course, we realized after the fact that we really started with a difficult surface with all the oxidation channels that silicon has, but at least this shows that we can have some qualitative understanding of the chemical reaction at surfaces in the presence of bias. Okay, I have 1 minute. So in 1 minute, I will tell you what we do about spin qubit. 1 minute is not enough, so I will take 3 minutes. So what about this, Giovanni? Okay, 4 minutes maybe. Okay, so, okay, 3.5. Okay, so 3. The question that we ask here is how can we design defects for qubits? So when you want to design defects for qubits, you want to understand the stability of your defects, and the stability of your defects, for example, at realistic condition, also in terms of strain. You want to do electronic structure calculations, and they need to be accurate. They need to be very accurate. This is why we worry so much about having electronic structure calculation that are accurate to position the energy level. And then you have to be able to do intra-defect optical transition. Very difficult. That's why you need optical spectra, photoluminescent spectra. So then, and this is the very, you even have, 2 minutes. Okay, fine. And then, what really, if you have all this figured out, you need to ask, okay, I excite my spin defects. Does it stay there, or there is a decoherence effect that ruins what I want to create to be entangled with somebody else? And one decoherence effect is the interaction with all the nuclei. And so to understand the interaction with nuclei, we built spin Hamiltonian, and we did a spin dynamics through the evolution of the density matrix using cluster correlation expansion. So I don't have time to tell you about this, but I want to tell you about our latest result. So we built this spin, so stability, DFT, electronic structure, many-body perturbation theory, and then some many-body perturbation theory to build your spin Hamiltonian. You use this to do spin dynamics, and then you compare with experiment for 3D materials, and for 2D materials, we have been able to make predictions. Prediction of the decoherence times for a specific 2D material, there are sulfur vacancy there. And we obtain a result that, in my opinion, is very important. And we proved that, for this material, we showed that the isotopic purification is much more efficient in 2D than in 3D, and you may have exceptionally long coherence time. And we were super excited about this, and we went to our friends experimentalists, and we told them, we will change the world with the 2D materials. You have to do this. So what about stop doing silicon carbide? And they looked at us and said, what are you talking about? Okay, so the problem is, and now we are addressing this problem, is that every time you have your defects, they are encapsulated into something else, and you now need to understand what this something else does to your coherence. And the preliminary results that we have are not super exciting, because you need to go to very, very large distances, more than 10 nanometers, to not destroy your coherence. Okay, I showed you that we are actually becoming quite good to give insight into the scripture and mechanism for materials. As Charles Coulson used to say, give us insight, not numbers. We are giving some insight. However, if you want to design materials, you need numbers. And actually, you need a lot of data. And so, of course, for interfaces and defects, we need to become much, much better and at generating much faster a number of more reliable data. I put references everywhere to all the work of the people of my group. I have many senior collaborators. This is my funding, and happy birthday again, CECAM. It's not too bad. I'm not, okay. Of course, I'll be happy to answer any question you may have.
Thank you, Giulia, very much. Please.
Okay, I would like to draw your attention that it is not so necessary to go to hybrid function in order to improve calculations and level of DFT in finite field. Where exists a rigorous way. Do you think about using optimized effective potentials, orbital dependent function? In this case, one can clearly show, and we showed in our papers, that in finite field, there is built-in counter field in response of exchange correlation potential or in exchange correlation kernel. And this is the crux in order to improve. So you see, you apply field, and in potential, proper potential, not hybrid, but orbital dependent optimized effective potential, you have counter field, right? That's very important, right? So it provides proper effect. Do you think about this level of theory, optimized effective potential?
No, we didn't think about that, and
But
maybe it's something that we should think about. Keep in mind that in spite of the fact that these hybrids are still kind of computationally expensive to get, these are, especially the one not for interfaces, among the simplest hybrids that you can get, with all the good things that come by being simple, and also some of the bad things that you don't get all the properties probably that you want. So these are simple hybrids.
yeah, I would like to just to draw your attention.
Sure,
Because
thank you.
In my opinion, hybrid function is a poor man's solution, right? In fundamental theory. Okay.
Francesco.
A question. You show the absorption spectra of ice, and in the experiment the gap is sharp. Instead you have in the calculation there is a tail going in the gap. Mm-hmm. Is this an artifact of finite size of a method? So can you comment about that?
Yes. Okay. Of course, every time you show something about water, there is always an expert, right? So you cannot get away with anything. Yes, you're right. For reason that I'm sure you know very well, we are worried about that. And this is exactly one reason why we did finite size effects. And these are 64 atoms. No, these are 96 water molecules, proton disorder. I'm not showing it there because the results are not very statistically significant. We also did a slightly larger sample, and we still have this. There are states that, because of the proton disorder, come down that the experiments don't have. And we need to understand what's going on there.
Could be that it's the snapshot method that somehow don't conserve energy in the exchange with.
No, but I mean, for ice, the snapshot method is a Monte Carlo method. So we generate proton disorder, the configurations.
Then you don't conserve energy in the transfer between light and the ensemble.
Oh, I see what you're saying. Okay, I see what you're saying. Yeah, it could. Yeah, I mean, yeah, this is not a solved problem. It's a good question. I don't have a correction yet. I mean, I have, okay. So I can make this come out right. If I pick, I can tell you, if I pick my snapshots, and if I do an ordered ice that we did, this will come out right. But I know it's not right, because experimentally ice is proton disordered. So I don't have a good answer.
This is Dielectric constant. This is very intriguing. You know the papers of Del Sole, right? You run into...
I mean, I know many papers of Del Sole.
Yeah, he thought about it for a long time. You run into this problem of the difference between the longitudinal and the transverse dielectric constant.
Yeah. So, yes, we do. So, okay. So if you were to do this, and actually we did, for an interface, for example, where you have a piezoelectric material like aluminum nitride, you have to have certain type of corrections that we have not yet been able to apply. And the examples were carefully chosen for silicon and water. There was another example where we saw this problem that was there, and this was silicon nitride. There are corrections that we need to apply. We have a system where these corrections have been applied and works well, which is silicon nitride, in which we have not only applied the field in one direction, but we have done simulation when we have applied the field in different direction. We have average and apply correction. I think that this can be worked out properly also for other types of materials. But this is very recent, so we don't have everything figured out yet. But you are right, and we are aware of this, and we are actively working at generalizing this also at piezoelectric materials, also because we want to use this for defects in piezoelectric materials interface. We are interested in aluminum nitride silicon carbide interfaces, and this problem is there.
It is almost the proper time to close, but there is an announcement by the director.
Julia. Before we all go for a coffee break, just this morning I knew that there will be one speaker who will not make it this morning. In the parallel session after the coffee break in biophysics and biochemistry, the talk at 12 by Marie-Christie Soli is cancelled because she's ill and she will not be able to come. We don't change anything else in the program, but just keep that into account when deciding how to organize yourselves, and especially for Francesco. Yeah? And now this is the time for the coffee break, and we reconvene at 10:30. Remember, it's important that we keep time. Yeah.